Hello there, students and friends. Welcome to part 3 of my lecture series on alternating current circuits. This episode focuses on power in AC circuits. We all know that alternating currents play a central role in systems for distributing, converting, and using electrical energy. So it is important to look at power relationships in AC circuits. How do we determine the power in each circuit element? In the resistor, in the inductor, as well as in the capacitor. You will find this out in this episode. So just stick around, watch, and learn. Supposing the circuit element is a pure resistor capital R, then the voltage capital B, which is equal to the voltage across the resistor, and the current small I are said to be in phase. Alright, so we have the graph that represents the power small p, and this is determined by multiplying the heights of the graphs of voltage small b and current small I. Alright, in the figure, this is at any given instant small t. The result is the block curve in this figure. There it is. That's the curve for the power. The blue is the curve for the instantaneous voltage, and this one here is for the current instantaneous, right? We say that the product of the voltage V, small v, and the current, small I, is always positive. This is because the voltage, small v, and the current, small I, are always either both positive, alright, or both negative. Hence, the energy is supplied to the resistor at every instant for both directions of the current, small I, even if the power is not constant. Alright? So, to get the average power P sub B, we just get 1/2 of the product of the voltage amplitude and the current amplitude, or 1/2 capital B multiplied by capital I. This is true for a pure resistor. And in terms of the RMS value for the current as well as the RMS value for the voltage, we can also express the average power being equal to the product of the RMS current squared and the resistance big R, or can also be in terms of the RMS value for the voltage squared divided by the value of the resistance big R, or simply the product of the RMS voltage and the RMS current. And maybe you are familiar with uh, the formulas for power in a DC circuit. You will notice that the formula for determining the average power in an AC circuit is just parallel, okay, to those in the DC circuit. Alright, so we will be talking about the power in an inductor. As shown in this graph, the voltage V sub L, meaning the voltage across the inductor, leads the current by 90 degrees, right? So when we multiply the curves of the instantaneous voltage by the instantaneous current, the product Vi is negative during the half of the cycle when B and I have opposite signs. The power curve shown in this figure is symmetric about the horizontal axis. It is it is positive half the time, all right, and negative the other half. So we say that the average power is equal to 0. And when the power is positive, we say that the energy is being supplied to set up the magnetic field in the inductor, right? And when power P is negative, the field is collapsing and the inductor is returning energy to the source so that the net energy transfer over one cycle is equal to 0. Now, in the case of the power in a capacitor, as given or shown in this second graph, all right, the voltage V of C, or voltage across the capacitor, lags the current small I by 90 degrees, all right? The figure shows the power curve, all right? This is the power curve. The average power is again equal to 0. All right, and the energy is supplied to charge the capacitor, and then it is returned to the source when the capacitor discharges. So the net energy transfer over one cycle is also equal to 0. In any AC circuit with any combination of resistors, capacitors, and inductors, the voltage V across the entire circuit has some phase angle, angle phi, with respect to the current small I. And if we look at the graph, all right, we have here the graph for the power, for the voltage, and for the current as functions of time. If you notice, the positive loops of the power, all right, with respect to the horizontal axis, the area of the positive loop is greater than the area of the negative loop, all right, which means that the average voltage for a complete RLC circuit connected to an AC source, we say that the average power has what we call some phase angle phi, all right, and this average power is just given as one half of the amplitude of the voltage multiplied by the amplitude of the current and the cosine of the phase angle phi, which in terms of the RMS values for voltage and current, it can also be equated to the average power is also equal to the RMS voltage multiplied by RMS current and the cosine of the angle phi. So each of these quantities in this equation is given here. All right. Um, the cosine of the angle phi, all right, is given the name power factor of the circuit. All right. It is a pure number, and there are three cases. When you are talking about a pure resistance where the angle P is equal to 0, the cosine of 0, as we know, is equal to 1. So therefore, we say that the power factor, all right, the power factor is just equal to 1. And that's the reason why the formula for the average power in a pure resistor is just equal to 1/2 the product of the voltage amplitude and the current amplitude. But for a pure inductor or capacitor whose phase angle P is either positive or negative 90 degrees, all right? For the pure inductor, we know that the voltage leads the current by 90 degrees, while the capacitor, the voltage in the capacitor lags the current by negative 90 degrees. And if you're going to determine the cosine of 90 degrees, whether positive or negative, it is equal to 0. That's why we said earlier that the average power in a capacitor or in an inductor, all right, is equal to 0. Now, for this kind of circuit, RLC series circuit, the phase angle P is also defined as the ratio of the resistance big R to the impedance capital Z, right? So big R is the resistance in the circuit divided by capital C, which is the impedance. A low power factor, which corresponds to large angle P of lag or lead, is usually undesirable in power circuits. The reason is that for a given potential difference, a large current is needed to supply a given amount of power, which results in large I squared R energy losses in the transmission lines. For our question number 1, in operation, an electric toaster has an RMS current of 3.95 amperes when plugged into a wall socket with RMS voltage 220 volts. Question: find the toaster's letter A average power, letter B maximum instantaneous power, and letter C resistance. So our solution, we assume that the toaster is a pure resistor where the voltage and the current are in phase. And that means also that the phase angle phi is equal to 0. So the average power, all right, is just equal to the product of the RMS voltage and the RMS current multiplied by the cosine of the angle phi. But since angle phi here is equal to 0, all right, the cosine value of 0 is understood to be equal to 1. And therefore, when you substitute, that's simply average power is equal to the product of the RMS voltage 220 volts and the RMS current 3.25 amperes. The answer to letter A, the average power in a toaster is equal to 869 watts. For question letter B, we are asked to find the maximum power. All right? So, the maximum power can just be taken by multiplying the average power by 2. In short, um, the maximum power is twice the average power. So that means twice the value of the average power of 869 watts. So the answer for letter B is 1738 watts. Now for letter C, we are asked to find the value of the resistance big R in this toaster. Okay, we simply divide the RMS voltage square by the average power. That is 220 volts square divided by 869 watts. And the value of the big R, resistance R, is equal to 55.7 ohms. Question number 2. An RLC series circuit has a source with voltage amplitude 35.0 volts and an angular frequency 1.30 times 10 to the third power radian per second. The resistance is 275 ohms. The inductance is 82.3 millihenry and the capacitance is 1.10 microfarad. Question letter A. Find the inductive and capacitive reactances. Letter B. The phase angle. Letter C. The power factor. Letter D. The impedance. Letter E. The current amplitude. And question letter F. Find the average power delivered to the resistor. So for letter A, our solution, the formula for finding the reactive or the inductive reactance, capital X sub L, is just equal to the product of the angular frequency omega by the given inductance, capital L, or 1.30 times 10 to the third power radian per second multiplied by 82.3 times 10 to the negative 3 Henry. And we get the inductive reactance equal to 107 ohms. Now for the capacitive reactance, capital X sub C is just equal to the reciprocal of the product of the angular frequency omega and the given capacitance, or 1 over 1.30 times 10 to the third power radian per second multiplied by the capacitance of 1.10 times 10 to the negative 6 farad. So we get the value for the capacitive reactance equal to 699 ohms. Moving on to question letter B. Alright, you're looking for the phase angle phi, whose formula is just equal to the arctan of the difference in the reactances, XL minus XC, divided by the resistance big R. So substituting, we have arctan of 107 ohm minus 699 ohms to be divided by the big R, 275 ohms. Using your scientific calculator, we will get the value of the phase angle P, which is negative 1.14 radians, whose equivalent in degrees is equal to negative 65.1 degrees. And for question letter C, we are looking for the power factor, which is simply the cosine of the angle phi, or cosine of negative 65.1 degrees. The power factor in three decimal figures is equal to 0.421. It's a unitless number. For letter D, we are looking for the impedance, capital Z, okay, using the formula square root of the square of capital R plus the square of the difference between the XL and XC, or the inductive reactance minus capacitive reactance, get the square. All right, substituting, we have square root of 275 ohms square plus 107 ohm minus 699 ohms, then get the square of their difference. We will get the value for the impedance equal to 653 ohms. And for question letter E, we're asked to find the amplitude or current amplitude, capital I, is just equal to the ratio of the voltage amplitude by the value of the impedance, or we divide 35.0 volts by 653 ohms, and we will get the value of the current amplitude already expressed in milliampere. It's 53.6 milliamperes. And for our final question, we are asked to find for the average power. All right, using the formula, the square of the root mean square of the current multiplied by the resistance big R. But since we don't know yet the RMS value for the current, we determine it by just dividing the value of the current amplitude that we obtained in letter E divided by the square root of 2. All right? So that means 0.0536 amperes divided by square root of 2, we get the RMS current equal to 37.9 milliamperes. And so therefore, the average power can now be determined by just multiplying the square of the RMS current, 0.0317 amperes, square it, and then multiply it by the value of the resistance big R, 275 ohms. So we will get the average power equal to 0.395 watts. And that completes our video tutorial for this topic on power in an RLC circuit connected to an AC voltage supply. Thank you very much, as usual, for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.